Let us continue our discussion here with some examples how in nuclear medicine diagnostics works. We will point out the role of the carrier molecule because it is very important. We will also have a short outlook to how MRI and the CT work. In the very first example, you will see it is a pretty complicated case, but it is a very important one because this is how we can recognize tumor cells. Tumor cells, first of all, always have some receptor molecules on the surface of the cell, and if you are smart enough to find another molecule which can form a strong bond, a strong chemical bond with this receptor, then you are done. And this is such kind of a molecule for certain types of tumors. So this molecule is like with this receptor molecule as a lock and the key. So this is a very strong bond. So once you have this, then you have a tool how to find the tumor cell. Okay, but this is not yet a radioactive isotope, and we are in nuclear medicine. We would like to bring indium-111 to the tumor cell, to carry it somehow. But this molecule itself cannot carry directly indium, so we need another molecule, which is an indium carrier molecule in this case. You see, this is a pretty complicated one. This is a diethylene triamino pentaacetic acid. Pretty complicated, you can safely forget. The point is that this molecule has 1, 2, 3, 4, 5, 6, 7, 8 molecule sections which can coordinate to the indium. So this molecule can grab the indium very firmly. And since molecule contains carboxyl groups can form a very strong bond with the amino end, here or here, I don't know, the amino end of this polypeptide. So there is a strong chemical bond between this molecule and this molecule. This is the tumor cell finder, and this will carry the indium because it still has 7 different groups which can grab the indium very firmly. That's it. And the indium is as a gamma emitter, and this is why it can be used for diagnostic. You may remember from the previous slides that indium has an electron capture decay. So this is a very well developed technique to find tumor cells. This is another example, a relatively simple example. If you want to image the bones of your body, then you may use technetium 99M. And as I said, technetium is very versatile, so you can use it for this purpose too. However, technetium itself wouldn't like to be absorbed on the surface of the bone, so you have to do something. And since bones are composed mostly of calcium phosphate, if you synthesize a phosphonate complex to the technetium, then these phosphonate or phosphate groups, whichever I use, they can be bound to the calcium content of the bones. It is a very nice thing. You will see that the bone structure can be seen also with using the traditional X-ray imaging, but you know, here technetium gets absorbed on the surface of the bone. And if there is some problem with the bone, say there is some inflammation, then the technetium absorption will be different. Okay, and so this difference will not be seen by normal X-ray imaging, but with technetium it will give the doctor an extra information on the healthy or maybe an unhealthy state of the skeleton of your body. Now we arrived at probably the most important technique in nuclear medicine, which is capable to find, with which you are capable, the medical doctor is capable to find a tumor cell, a tumor in the body. This is positron emission tomography. In the previous example, we needed some receptor finder molecule to find the tumor, and only for a special tumor. Positron emission tomography does not require a special receptor. Let us see how it works. So this is really good to sensitively locate the tumor, in almost any type of tumor, and it is also good for brain research. We will not discuss this in detail. What is a radio tracer? This is a fluorine 18, a positive beta emitter, which has a relatively short half-life, so we should be hurry a little bit, but this is not a problem now. The radiopharmacon, so the molecule which is labeled with fluorine 18, is actually glucose. You can safely forget this complicated name. Just remember that is the typical and regular glucose. However, one OH group, here originally there would be an OH group, this is replaced with fluorine 18. So how it works? You know, tumor, and any tumor, they need a lot of energy for cell propagation. Therefore, the glucose consumption is always high. The fluorinated glucose is carried to the tumor cell, but the metabolism of glucose gets stuck because of the carbon-fluorine bond. So this is a big trick. So we at least how to say mislead the body, because we give the body glucose. However, it is fluorinated, but the body, our biochemical process, they do not recognize that it is not real glucose. So they carry it to the place where energy is needed, and then they start to decompose, to metabolize the glucose, and then they realize, this is not glucose, and they stop. And the fluorine 18 is retained in the cell, and therefore it marks the position of the tumor. Now we just need an instrumentation how to locate the tumor. As we discussed, fluorine 18 is a positive beta emitter. That means it will emit positrons, and after thermalization, these positrons will have an annihilation with electrons giving 2 gamma photons. This is called positron annihilation. This positron annihilation results in these 2 gamma which are emitted in opposite directions. So if you set detectors around the patient in a circular manner, then in this example, for example, the 2 yellow detectors will detect these gamma photons simultaneously. So you know that the annihilation took place somewhere in between the 2 detectors. In another occasion, maybe the 2 blue detectors will give a simultaneous signal to the detection system. If you record millions of such events, then the intersections of all these lines will mark the position of the tumor. In this example, I show you a brain image because brain can also investigated by PET method, because brain always consumes a lot of glucose. On the other hand, this is a problem because brain tumor may not be detected by PET, but any other tumors can. So here you can see a real PET image of the patient, and this is a very faint picture, so not very sharp. The problem is that the doctor sends the glucose to the position where the tumor cell is, but the annihilation takes place somewhere else because the positron should be thermalized, and it takes about 1-2 millimeter travel in the tissue. So that means that the position of the tumor cell will not be so well defined. It is plus minus 1-2 millimeter per millimeter. So this is a faint image, and normally the doctors combine this method with CT imaging. This gives you a very sharp image. This is based on X-rays. We will discuss it later. And when they combine the 2 images, then you get the perfect picture. And in this situation, unfortunately, you can see here this that probably a thyroid tumor is observed. So this is a combination picture already, a combination of PET, which is a functional imaging, and a CT, which is an anatomical imaging. Since we mentioned CT, let's have a short outlook how it works. CT is based on X-ray absorption. In general, the X-ray imaging of the human body is based on the absorption of X-rays by atoms of the body. In addition to the density, which is simply measured in gram per cubic centimeter of the tissues, the absorption strongly increases with the atomic number. This is a really very important dependence, and it is based on the photoelectric effect. We don't go into details. Instead, I just show you some examples. So if we compare the absorption ability to that of carbon, then for calcium it is 120 times higher. So the absorption of X-rays is 120 times higher in calcium than in carbon. For iodine, it is 6,000 times more effective, the absorption, and therefore it can be used if you get intravenously some potassium iodide injection. Then blood circulation can be followed in your body, maybe in the lung, in the kidney, in the brain, and so on and so on. So this is a typical contrast material. For calcium, I didn't mention, but of course this is the best thing to image the bones. Barium is also a very heavy element, just like iodine, even heavier than iodine, and for that this difference in absorption is 7,500 fold. So it is absolutely good for a contrast material, especially if you want to investigate your stomach or the intestine system. Then you get barium sulfate. It is interesting that barium is a very poisonous material, it's a very poisonous metal. However, barium sulfate is so insoluble in water that it is absolutely safe. So you just eat some barium sulfate and your stomach and intestine system is imaged by X-ray investigations. This is regular X-ray imaging. Okay, you just need an X-ray tube and some recording material, and that's it. What about CT? This is computed tomography. So this is a combination of partial imaging, I would say. So the X-ray absorption is measured by using thin X-ray beams from various directions. So we check the absorption of the body, the absorption of X-rays in the body from various directions, and we do a very large number of such measurements, and therefore a spatial distribution of the absorption by the bones or any contrast materials can be visualized by the appropriate computer software. So this is the most developed, the most progressed technique for X-ray imaging, the CT, and this is very widespread now in medical practice. When we discuss the CT, we could see that CT uses harmful radiation, actually X-rays, which are ionizing, which is an ionizing radiation. Luckily, we have an alternative method which is called MRI, which uses no radioactive material, no radioactive substance at all, and no ionizing radiation. This is magnetic resonance imaging. Let us have a short outlook to see how it works. Actually, this is nuclear magnetic resonance imaging. However, the word nuclear may be a little bit frightening to people, so that's why normally it is omitted. So we just call it magnetic resonance imaging. Nuclear magnetic resonance is possible on atomic nuclei that have magnetic moment. The simplest is the proton, the nucleus of the hydrogen atom. So this is non-radioactive, let me emphasize. The protons, as tiny magnets, can absorb and emit energy when the magnetic poles are forced to turn to the opposite direction and then turn back, respectively. This force is applied by non-harmful radio frequency radiation, while the body is placed in a very strong, also non-harmful magnetic field. The magnetic resonance occurs on the protons, so MRI basically produces a 3D distribution of the hydrogen density in the body using the same technique as CT, but with a radio frequency radiation instead of the ionizing X-rays. Please note that when we use X-rays, the X-ray absorption is high if we have heavy atoms like calcium and iodine we mentioned, or we mentioned also barium as a contrast materials. So the higher the atomic number, the higher is the X-ray absorption. For MRI imaging, we measure the lightest element, the hydrogen. So actually we measure the hydrogen density distribution in the body. MRI is mostly anatomical imaging, but this is the highest resolution technique available today, and this is why it is so important. Thank you very much for your attention.